Science students, welcome to our lesson on geologic time. When we're studying what has happened in the past, it's important to know that what happened in the past is similar to what is happening currently. So that is this idea of uniformitarianism. This basically states that the things that happened in the past geologically are the same as what's happening right now. So any of the processes like weathering, erosion, volcanic eruptions, those all happen the same way in the past as they do today. And the root of this word uniformitarianism is the word uniform from the Latin uniformis, meaning having only one shape. So in this case, uniform means the same. So the processes today are the same as the processes that happened in the past. Let's begin our study of geologic time with the process of relative dating. Relative dating is a practice that we can use to tell the order that things happened in. Relative in this case means like relative to something else in relation to something else. So we can tell how old things are relative to one another, but we can't actually tell their exact age in years using relative dating practices. The first relative dating practice that we'll discuss is called this law of superposition. The law of superposition basically states that when rock layers formed and then when they're left undisturbed, the ones at the bottom of a segment are going to be older than the layers at the top. So like for example, in this picture, oldest layer at the bottom here, youngest layer at the top here. And then we can use this to date things that are included within those layers. So like for example, in this particular chunk here, we know that the fossil of this shell is older than the fossil of this snail because this shell is found in a deeper layer than the snail fossil. Next practice we have for relative dating is called the Law of Original Horizontality. So this seems like a lot of words here, but really it's just saying that originally layers of sedimentary rock formed in flat horizontal layers. And if there's any kind of tilting or disturbance that happened after deposition and after those rocks were already formed, so like in this picture here, initially these rocks formed in nice flat layers and then some geologic process happened to push them upward. They didn't form in curved layers like this. They formed in flat layers and then something happened later to push them up. And then I put this picture in here because I'm sure we've all seen this. This is on the drive to Missoula, and there's this big cliff face that has these really foldy rocks in here. So again, all of these layers formed completely flat, and then when these mountains were being built, something squished them together, and that's how we got the folds and bends in the sedimentary layers here. And next we have what's called the principle of cross-cutting relationships. This basically means if there's anything that's cutting through some layers of rock, the thing that's cutting through is younger than the layers of the rock. Of course, this makes sense because how could something cut through layers of rock if those layers of rock weren't already there when the thing began to cut through? So this typically we'll be talking about this word inclusions. An inclusion is just a chunk of rock that's inside other rock that it's not wasn't initially part of when the original rock formed. So for example, igneous things like sills and dikes and batholiths could be considered inclusions. And like in this picture here, we've got the law of superposition telling us that this layer is older than this one. And then we have the principle of cross-cutting relationships showing that this, I guess this would technically be a dike since it is more perpendicular to the layers, that this igneous dike is the youngest layer because it's cutting through these older layers. These older layers must have been there when the dike formed. And next we have correlating rock layers. So basically we can look in different areas that have been separated by, maybe there's like a river canyon going through here. We can tell that layers of rock are the same general age based on the specific kind of rock that it's made out of. So if it's like a really chemically specific type of limestone or something like that. Or also we can look at index fossils that are contained within that rock layer. Index fossils we'll learn about more later, but basically they're an organism that only lived for a short period of time, but they lived over like a wide portion of the earth. And so if you have that index fossil inside of rock, you can get pretty close to the age of the rock because the index fossil didn't exist for a very long time on the earth. And now we'll move on to relative dating practices that are about unconformities. Unconformities are breaks in the rock record. So typically rocks will be like sedimentary rock layers will just be deposited in a bunch of flat layers, and then some kind of unconformity will be visible when that deposition of flat layers of sedimentary rock stopped or changed. First, there is the angular unconformity. This is when you've got tilted or folded layers that are deeper, and then there's like a distinct boundary in between, and then there's those flat layers deposited above. So these tilted or folded layers underneath are at an angle to the new flat layers that have been deposited above, and so that is why it's called an angular unconformity, because these layers are at an angle to these newer flat layers here. And the next type of unconformity is called a disconformity. So now this is when there's evidence that deposition stopped and erosion was going on for a while. So here we've got flat layers of sedimentary rock, and then this boundary right here is called the disconformity because something happened. You can see right here that some erosion happened, like to this layer right here. And then after that erosion stopped, for whatever reason, the new sedimentary layers were deposited on top. So this boundary right here between the old layers that were forming from deposition, and then some kind of erosion happened, and then new layers started forming from deposition, that is called the disconformity. Then we have what's called a non-conformity. So this is the boundary between an igneous or metamorphic chunk of rock and sedimentary layers that have been deposited above. So in this case, this line here is the non-conformity. Typically on geologic diagrams like this, when there's like all these little kind of dashy slash marks in a rock layer, it's indicating igneous rock, so we'll just call this like an igneous batholith. And so this igneous batholith, the boundary between the igneous rock and the sedimentary rock above and around it, is called the non-conformity. So we can use the principle of cross-cutting relationships to tell that since this batholith is included within, like it kind of cuts through this layer and this layer, we know that these layers were present when the batholith formed. We can't tell for sure whether these layers were already there because maybe they were already there and the batholith just like, you know, didn't go up high enough, or maybe only this layer was there and these layers formed later. We can't quite tell exactly with those two layers based on this diagram. Alright, so everything we've talked about previously under relative dating was when we were comparing the ages of things relatively, so just compared to each other. Now we'll move into absolute, or also sometimes called radiometric dating. This type of dating can find the age in years of something like a rock or a fossil using the abundance of these things called radioactive isotopes. So the way that this absolute dating using radioactive isotopes works is that we measure the rate of radioactive decay. This is basically where we choose some type of radioactive element, a lot of times like rubidium or uranium, something like that. You choose an isotope that is going to decay because it has too many neutrons in its nucleus, so it's unstable. So over time, at a set rate, it will decay into what's called its daughter isotope. So like as this element loses stuff out of its nucleus, it turns into another element called the daughter. And then you look at the ratio between the amount of parent isotope there is in something and the amount of daughter there is to find the age. And the way that we measure these ages is by counting half-lives. One half-life is how long it takes for half of whatever the initial amount of parent isotope there was to decay into the daughter product. So we can look at these ratios here. So for example, we'll use carbon-14 as an example. I've got a star next to that on this table here because carbon-14, you should definitely put this in your notes, is the only one of these radioactive isotopes that we can use for things that were once alive. Carbon-14 is in things that are alive, and then it decays into nitrogen-14 after those things die, and one half-life of carbon-14 is about 5,700 years. So when 0 half-lives have passed, and like we're examining these isotope ratios in whatever the fossil is, it's still completely carbon-14 and no nitrogen-14 when that animal is still alive. But then after 5,730 years, exactly 50% of the isotope will still be carbon-14 and 50% of it will have changed into nitrogen-14. So we know that one half-life worth of time has passed. Same deal if you just picked up any fossil and you compared the amounts of carbon-14 and nitrogen-14 to each other, and you found, well, it seems like there's about 82.5% of the isotope in here is nitrogen-14 and 12.5% is carbon-14, then you can use that 12.5 to 82.5 ratio to see that 3 half-lives have passed, so that animal has been dead for a little over 17,000 years. So it's just half of the parent decays through each half-life. So like 50% turns it, or 100% turns into 50%, turns into 25, half 25, 12.5, half of 12.5 is 6.25. So it's just half of the original parent decays every 5,730 years. So that is how we measure the age of anything that has these radioactive isotopes in them. And now we'll discuss the geologic time scale. This is basically just like a graphical type of representation of everything that has occurred in Earth's history, both geologically and then the history of life on Earth. We can tell the history of life on Earth by looking at different kinds of fossils that are present at different time periods in the past. And we know that the Earth is about 4.6 billion years old according to the radiometric dating techniques that we discussed on the previous slide. We look at the oldest rocks we can find on Earth. We look at certain meteorites that formed at the same time as the Earth was forming about 4.6 billion years ago. And we can tell that the Earth is approximately that old. And remember, at the end of your notes, you're going to go watch that additional video that describes this in more detail. Alright, so the way that geologic time is divided is completely arbitrary and based on human discretion. Pretty much we look at the rock record and the fossil record and we look for like distinct times when something changed, and that's how we decided to divide everything up. So the time is broken up into chunks that are made of smaller chunks, which are made of even smaller chunks, and the longest of the chunks is called the eon. There's two eons, the Pre-Cambrian eon and the Phanerozoic eon. And so like, for example, this is the way that we decided to cut this off, like the way that humans decided that Pre-Cambrian time went until 542 MA means million years ago, is that right at 542 million years ago in rock that old is when we start to see fossils of stuff that was alive. And so that's what Phanerozoic means. It means, Phaneros means visible and zoic means life. So this cutoff is where we start to see fossils of stuff that was alive before. And then Pre-Cambrian, we call it Pre-Cambrian because the next, the period, the specific period called the Cambrian time where there was an explosion of life on Earth is what came next. The eons are then divided into smaller eras, and again, these divisions are typically because there's like some geologic event that happened at that time that like drastically changed the way that things were on the Earth, and so that's how we decided on those cutoffs. And the eras are divided into smaller periods, and typically these are based on, from fossil record, like what was the dominant life species like on the Earth during that time, and that changes periodically based on the change in, well, especially climate, like what kind of animals can be dominant at a given time changes based on what the conditions are like. So that's basically what these divisions came from. And then the shortest time period that we divide the more recent periods into are called epochs. I know it's spelled like it should be pronounced epochs, but it's epochs, and these are the shortest time periods. So if we look at this geologic time scale right here, this is kind of a standard format, but sometimes they'll be laid out differently, but they're always going to go in the same order. Like it's always going to be Cambrian, Ordovician, Silurian, Devonian, like that, because this is like a standard thing. So if we're looking at this time scale, we can tell towards the top is more recent. So this epoch right here, Holocene, is the one that we are in right now. So that's from 0.01 million years ago, is like 10,000 years. So from 10,000 years ago to now, we've been in the Holocene. And the Holocene epoch is part of the Quaternary period, which is within the Cenozoic era, which is part of the Phanerozoic eon. So we are in the Holocene epoch of the Quaternary period of the Cenozoic era of the Phanerozoic eon, and that is where we exist in geologic time right now.